recording. Lecture 25 will be mainly a continuation of the previous lecture. So it will be sensing the environment by cells. Okay, so I continue discussing the same paper I was talking about, but for cell. It's a classic paper in biophysics. This was Biophysical Journal, 1977. Okay, so on the last day, I was talking about, I do just a brief reminder. I was discussing a cell that is like a perfect instrument. So remember, we have like an antenna that can track in a sphere. It can measure all the molecules that are at the time t. Okay, the molecules can enter and escape this sphere. The sphere has radius a, and this is within a bigger container of radius r. This is what I was discussing the last day. And as I said, we are thinking about a device. It's a biological system which can measure m of t. So it can count the total number of molecules of a given species within the sphere. You can count this for any time. And from measurements of m of t, it constructs the time integration over a time window. So it does, it can count for a given fixed time and take averages. Okay, it's 1 over t integral from, we can say 0 to t, m of s ds. Okay, be careful that here it's not the same m sub t than m at t. Okay, this is like taking a photograph at time s and counting all the molecules that are at time s. And this one is a summation over a set of photographs from 0 to t and dividing by t. So it's like taking the average of how many molecules you counted at different times. Okay, and then we call this time integration. Okay, time integration. Okay, integration. And this is taking an average. Okay, this is an average over the time window 0 t. Okay, and as I said, this because molecules are diffusing in and out. This this one is escaping, this one is entering. This brings the fact that fluctuations make that m of t is a fluctuating quantity. So if I take these photographs at time 0, this is different than if I take, for example, I would take here plus a given time. So instead of starting now, I start 1 second later, t1. Okay, and this will give me different numbers such that this will be fluctuating. So depending on what is my t1, I will have a different number. On the previous day, I told you that from here, one can estimate the concentration. In the end, I was discussing the cell would like to measure the concentration in its environment, and the way you measure the concentration is, the way you estimate it is like this. So you do m of t divided by the cell volume. The cell volume is 4/3 pi aq. So in the end, I should be discussing the fluctuations of c, but in reality, the fluctuations of c is just the fluctuations of m of t. We just have to multiply by a constant, right? Fine. So on the previous day, I showed you that, first of all, the average of m of t, it's well known because we know that the real value of c bar, is related to the expected value of m of t. So this is just like this. This is just a reminder, a cube, such that the average of m of t is given by this number, 4/3 pi a cube c bar. Okay, this was the first thing, but I'm mostly interested, and this is what I discussed the other day, on the errors and how precise can a cell, well, this is the perfect cell, so it can be better than this. How precise can be the measurement of a concentration if you have a device that counts number of molecules? right? So this is what I try to explain, to start explaining the other day. So I define, I'd like to know what is this, okay? This is the variance, mt squared minus mt to the square. Okay, this one is easy. I know average m of t squaring is easy. What is more complicated is this one. Okay, this is what I started to calculate on the other day. So I want to compute this. This is the variance. The variance. Why I want to know this? Because then with this, I will know what I'm interested in this quantity, delta mt divided by mt, which is the standard deviation, the square root of the variance, which will be mt squared minus average of mt to the square divided by mt. Okay, this will be the goal of today's lecture, computing this fully. All right, on the other day, so now what is important for us is mainly we know average of m of t is this, which we have here and here. We don't know the average of mt squared. This is more challenging. This is what I started to compute on the other day. All right, so the average of mt squared, remember mt squared, as I gave you that trick, multiply with s and s prime. So mt squared, it is equal to 1 over t squared. And then be careful here. So we will do in this way, ms ds ms prime t s prime. This is the object that I'm interested in calculating. Of course, if I want to do the average, I do an average here, it will be, this is deterministic, this is deterministic, so the average in reality will be of ms times ms prime, because m of t fluctuates. So then we can write this in a bit cleaner way. If we want to do the average, we just do the following, which is integral ds prime integral ds 0t ms prime. And we called this one, we call it g of s minus s prime. Okay, it's just a definition. On the other day, I showed you that this g, okay, let me go a bit down. This g of tau, well, let me call this by now tau. G of tau is, it can be split in two terms. So the first term is easy and the other one is more challenging. So the calculation that I reached was the following. The first one was, well, it's an approximation. We calculated one of them, because remember, here we have to count the total number of molecules, and we said that in a full container, there are, okay, in a bigger space, there are total n of molecules. So we were doing the correlations of the occupation of one molecule with another. So we were counting cross terms, and we were counting also self-interaction terms. So what is the probability that a single molecule that was here at time t, it is later also inside this volume at a later time. The first term of interaction between, cross correlation between two molecules, we calculated in the previous lecture, and it was just this quantity, and a cube divided by a cube squared. Actually, we showed it was even easier. So in reality, what we showed, it was that, okay, give me a second, we showed, it was very simple. It was just mt squared. And the second term was more challenging. It was mt times u of tau, sorry. U of tau, okay, be careful with these and taus, but m of t, it doesn't matter if with t, tau, whatever. So it's taken over this time window, and it doesn't matter which is the origin of the time, okay? We assume this is stationary. U of tau was the quantity we were interested in computing, and this quantity was the probability that a molecule initially sampled with uniform distribution in this sphere, probability that the molecule is inside the volume time t, and it diffuses, whatever, and it's also inside the volume at time t plus tau. Okay, this we can also maybe call it survival in a way, probability. Okay, well, I put it like this because in reality there are no absorbing boundaries. So it would be survival if there will be an absorbing boundary. So the particle escapes and it's annihilated or evaporates. It's not like this. It's just the probability that at a later time, so tau time later, the probability is here inside. Okay. So, okay, very good. Then, okay, if I go back to the calculation, I give you, so I wrap up, and what I was doing is this calculation, m of t squared. So I recovered the result from the last day. It's 1 over t squared, the integral 0 t ds, the integral 0 t ds prime. And then this one, I said is mt squared plus mt u tau. So it's, and I can also write it like this, m squared plus m, and then it's s evaluated at s minus s prime. So it's u evaluated, well, tau is s minus s prime, so it's the same thing. Okay. So now when we integrate, this is a number that we know how to calculate. This is a number that we know how to calculate. So then the integral, the first integral is just integral over t, t times t is t squared, they cancel. So you just get mt squared. And the second, we take out this one. There are two t's that go. Well, actually, no, you cannot do it because there's s prime, s prime. So you have to keep it like this, mt. Then there is 1 over t squared. And then integral 0 t ds, integral 0 t ds prime u s minus s prime. Right? So this is the quantity I'd like to compute, and I will call, it's a lot of noise here, I will call all this, I will call it g of t. Okay? You see that we are integrating over s prime over s, so the only variable that will survive here is t. Okay, this will be a function of t. All right, so let me continue with this. So I'd like to compute g of t given by, okay, give me a second. I did a mistake here. I will call g of t, just to be consistent with my notes. I'll call g of t, oh, sorry, to the following. This is 1, and I call g of t to the second part. I won't take into account t squared. Okay, this is what I call g of t. The t squared is a prefactor. I took it out. All right. So g of t for me will be the integral 0 t ds, the integral 0 t ds prime u of s minus s prime. So the first thing I realize is that this is symmetric. If I change s minus s prime by s prime minus s, I have the same thing. So I just said u of tau equals u minus tau. There's the symmetry property. So this means that this integral that is done over s and s prime, this is, I'm integrating 0 to t, so s goes from 0 to t, and s prime goes from 0 to t. Okay, so in the end, I'm doing an integral over a square. Okay, this I can write it like as an integral over a square of the s square. Okay, it's a surface, it's an integral over this surface. But because of this symmetry, I can reduce this integral to the rectangle. Okay, can do something like this. So this is written as twice, the integral of the square is twice over the integral of the rectangle, 0 to t. So I integrate s from 0 to t, ds, and s prime, I integrate, well, actually now I'm taking actually this part, okay? So forget about these lines here. I will integrate over the part that is above, so this one. But it doesn't matter, it's symmetric. So I will integrate s prime from s to t. S to t of s prime. And then I put here u of s minus s prime. Okay. Now it comes, in this paper, they bring another assumption. So again, I will call this tau. And there is a big assumption that is assuming that this function decays fast. Okay. So there is an assumption. Well, actually, the assumption is the following, that the assumption is that the observation time t is much larger than the characteristic time, we call it tau 0, it's a characteristic time of u of tau, okay? So the idea is that u of tau decays with tau, so this function here, u of tau decays something very fast compared to t, okay? So what I'm saying is that u of tau will be, we will approximate it as an exponential, where the mean will be at tau 0. This is what is called the characteristic time. And our time window in which we measure is much larger than this. So when you have something like this, okay, so we are saying we are approximating, actually I'm trying to follow the logic of the paper, but it's not so clear when you read it. Okay, this will be approximated like this. S minus s prime divided by tau 0. Okay, and then I will say t is much larger than tau 0. So I can change this integral by, it's an approximation, by the integral from 0 to infinity. So by 2 integral 0 t ds, and then I will say integral, I do the change of variable, so now I go d tau, okay? So when s prime equals to s, tau equals to 0, and then I will say t is very large, so I will take this integral up to infinity. Because t is here, so it doesn't matter, I integrate over a small window like this, or over 0 to infinity. This is the approximation they do. And then I'll say, okay, this will be like e minus tau over tau 0. And if you see here, if you do the integral, this integral here, 2 with this becomes 2 tau 0 times t. Okay, this is under this approximation. So if we do this approximation, and I go back here, this will be approximately equal to 2t tau 0. Okay, so the t, you can cancel with this. So this part will become 2 tau 0 divided by mt. So under this approximation, mt squared becomes mt to the power 2. This is what we have here. This was exact. And this is the approximated part, which is plus 2 tau 0 divided by t times mt. Okay. Recall that this is much bigger than this, so this will be in reality a small number. Okay. And then what is tau 0? It's the only thing we need to compute. Tau 0, in reality, I'm saying that is the integral from 0 to infinity of this, which is u. So it's the integral from 0 to infinity of d tau u tau. Okay? And this, in reality, all the problem of calculating mt squared will become in computing this tau 0. Because mt, we know, this we know, this is a number, this number, we just need to compute this. Okay, so all in all, if I do the variance later, okay, empty square minus empty square, it will be this part. This minus this will be just 2 tau 0. This will be the variance that we are trying to compute, okay? Just this one. This is what we want. So all the problem becomes now in understanding what's the value of tau 0. So if we know tau 0, which is this integral of the survival probability, then we will know what is the variance of m of t. Okay, this is the variance of m of t. All right. So the next part of the lecture will be about computing this integral. Just computing the integral from 0 to infinity of the probability. Remember, u tau is the probability that the particle was in the sphere, and then it is in the sphere at a time that is tau later than the initial time. Okay, and this is not so simple neither. So you can find it in the appendix of the paper I'm discussing. So let me go now into this one. There will be, this part will be calculation of tau 0. Integral from 0 to infinity of u tau d tau. Okay, so let me try to go into this and to explain it in simple terms. So in order to do this, what we will assume is we need to know first this quantity. So we start, as I said, with a sphere field of molecules. The sphere has radius a. We say at time t equals 0, we have the sphere of radius a is uniformly filled. So there is a homogeneous distribution inside the sphere, and the question to know this is how many molecules which were initially in SA remain inside the sphere at time t equals tau. Okay, this is the question I would like to solve. Okay, so how do we attack this problem? Well, mainly the only thing we consider here is diffusion. So from diffusion, this is three-dimensional diffusion. Okay, remember in my course I was focusing much more on 1D diffusion, but this is an object that is three-dimensional, so we have to take into account the three dimensions. Three-dimensional diffusion. Okay, in 3D we know that we can solve the Fokker-Planck equation exactly for a diffusion without the drift, also with drift in simple cases. Okay, so we can think about, for example, if you put a source of molecules at r equals 0, where r now is the radial coordinate. So if you start like this, er0, at time 0, all my molecules are in the origin. It will be this. So this is delta Dirac at r equals 0. Then you know that the molecules will start diffusing. Okay, and this diffusion will generate like a Gaussian profile, as you know. It will be Gaussian profiling in 3 dimensions. So from the Fokker-Planck equation, if you solve it, you will get that the density of molecules that are at r, any r, time tau, is a Gaussian. R squared for the tau divided by 4 pi d tau to the power 3/2. Okay. Remember, we had some. Oh, this sound is so annoying. It's crazy. Remember when we had this in a line? So we were in a line. We were starting from x equal to 0 with a distribution delta x solving the Fokker-Planck equation, this was diffusing and getting a shape like this. So we have p x tau up to time tau is e minus x squared for t tau divided by, here we had square root 4 pi d tau. Okay, why there is a 3 here is because you are in 3 dimensions, so you have to have the right normalization. Okay, but this is nothing else than what I explained, but in 3, right? So now, having said this, we are almost ready to start calculating this quantity. So I'd like to know u tau. So what is u tau? U of tau will be the following. We have a certain amount of mass or number of particles at time 0. And we have to compute what is the remaining mass or number of particles inside the sphere at time tau. And the way we do this is the following. So what we will say is that the following. So we have initially, there's a uniform distribution. So we will have that here there is volume times density. We will say the particles have mass 1. So this will be volume times density. We call it density 1 initially. And the mass that we will have inside the sphere time tau will be the following. We will integrate over the initial volume and integrate over the final volume of how many particles remain. So the number of particles that will remain will be given by the diffusion law. So we will have P of R minus R prime. Okay, remember this is just with origin at 0, and this will be, we have the volume V, which is, okay, there's one, sorry, the volume V is centered at 0, and the volume V prime is also centered at 0. It's the same thing, but we are computing the integral over all the volume. So a particle initially can be here at an R that is different to 0, okay? And then at a later time, it can go to the same volume, but it can go to another position. So this will be in R, and this will be in R prime. Okay, if I want to be even more precise, in reality, we have here spherical coordinates. So, okay, let's say this is the sphere I'm looking at. This has radius A. So a particle can be initially, for example, here, and this will be x, y, z, the coordinates of the particle. But of course, we can pass this to spherical coordinates. So this will be r, theta, phi, okay? And then later on, it can go somewhere in the volume, which could be, for example, here. This will be x prime, y prime, z prime, which will have coordinates r prime, theta prime, phi prime, okay? That's why there is this thing here. So I'm integrating over all possible trajectories. I can start here and then here and so on. And the integral is done over this volume, sphere SA, okay? Something like this. And this will give me what is the density of particles that starting from R are in R prime, okay? Following diffusion. So it will be a formula like this, but changing instead of R, I'll put R minus R prime. This will be tau, okay? And that's it. And of course, here I should have done the same, but here is a time 0. So if I do d v prime, okay, actually, this. And then the computer is telling me if I'm playing music. There is this, this noise, and it's asking me this. Okay, so here you will have this one, p of r minus r prime 0. Okay, so if we do this, this one is delta r minus r prime. If I integrate now this if I integrate now over this, so then we will have, sorry, it's difficult to focus with this noise, it's very bad. So if I integrate over V, which is the volume, first integral will give me that R prime equals to R, and the second integral will give me the volume, okay? And just get this out of this integral. That's why I was writing here just the volume, okay? Here I'm doing the same, but I'm just changing the tau, which is the time at which I'm looking. So this one, all this story gives me in the denominator. Okay, I'm doing it very slow, but I think it's better. 5, 8, okay. So it all becomes in calculating this integral. So it's the integral of this function. Well, here we'll put R minus R prime absolute value over the volume R and over the volume R prime. And the volumes is the sphere with center at 0 with radius A. All right. So with this, we will know U tau, but remember, my goal was to compute the integral over tau of U tau. So in reality, my goal, okay, I think I need a new one. My goal was to compute the integral U tau d tau from 0 to infinity. And now I said, okay, U tau was, okay, here I'm going to use that U tau is integral dv prime volumes p of R minus R prime absolute value at tau divided by 4/3 pi e cube. Okay. But you see, one thing is from outside we have the integral over tau. So instead of doing first this integrals over volume and then do the integral over tau, we will do first the integral over tau because it's easier. So the integral, remember, this quantity here, if I had to write it explicitly, is dv prime, and then it's exponential of minus R minus R prime squared over 4 d tau divided by 4 d tau, 4 pi d tau to the 3/2. Okay, and the denominator we had 4/3 pi 8 tau, right? So you see, this integral is not so easy because you have to integrate in the spherical volume. So you have to do, I don't know if you remember, but these are an integral over 3D in spherical coordinates. It's not so trivial. However, if you see, we need to integrate this over tau, and the integral over tau doesn't look so difficult because it's an exponential with this. Tau is here, and then tau is in the denominator. So the integral over tau will be of the type integral d tau. It will be e. Well, it will be something. Well, actually, I can write it like integral over x that you are more used to. Okay. It will be dx e minus a constant divided by x. See, divided by x 3/2. And there will be 0 to infinity. This is the type of integral we need to solve here. And this integral can be done. This can be done analytically. Okay, so this is why this problem is interesting because we can solve it analytically. This is what I'm going to do now. So I'm going to integrate first over tau and then integrate over the volumes. So integrating over tau, what I'll get is the following. So let me call this rho. So I defined rho, it's R minus R prime, actually with absolute value. So this is the distance between 2 points. And so then this one will become, well, actually what I will do first, which is easier, is to, again, what I'll do first is to integrate. I will keep this constant for later, so I will first integrate just this one, okay? So here I will do first the integral the integral from 0 to infinity of d tau p rho of tau. Okay, so I'm taking this and integrate it over tau. How can we do this? So this is the integral 0 to infinity of d tau e minus rho squared divided by 4 d tau divided by 4 pi d tau 3/2. Okay. So an easy way to do this, okay, is calling. This is when you find this type of exponential integrals. A good trick is to call all this, to call it x. Okay, this is a change of variable. X will be rho squared divided by 4 d tau. Okay, so now this means that d tau, which I put here, d tau will be, so I pass tau to the left, I pass x to the right, and I take derivatives. So I will have that tau equals rho squared divided by 4 dx. This means I take derivative, and derivative d tau equals rho squared with a minus 4 dx squared dx. So if I take the derivative of 1 over x is minus 1 over x squared dx. All right. So you see that now this integral it simplifies because we will have this 4d that goes out. The x squared will be somewhere here, and then we have also to change the variable here. So you see tau will become rho squared divided by 4 dx. So there will be an x in the denominator here, 3/2 and x squared. So after all, what you get, I'm skipping a bit, you don't need to do a lecture of calculus, is something else, physics is our goal. So this becomes pi 3/2. So this is a prefactor that comes out. And then you get integral 0 to infinity of dx is e to the minus x, and what remains here, there is an x squared. So there is an x squared that appears here, and this is tau to the 3/2. So this is x to the minus 3/2. So what survives is just here square root of x. Okay, this is what you get. So there is a prefactor times this integral, and this integral turns out to be known. So this integral is just square root of pi. This is a gamma function at 1/2. Okay, a square root of pi. So here there is pi to the 3/2. So it's pi to the 1/2 divided by pi to the 3/2 is pi to the 1. So all this integral becomes just 1 divided by 4d rho pi. Okay. With this, we calculated the integral of this over tau, and now we just need to, okay, there will be the rho, and we need to do the integrals over the volumes. So what we get is that tau 0 equals, okay, I come back, tau 0 was the integral over tau. Okay, this is what you want to calculate. Integral 0 to infinity d tau, well, actually it's here, I'm just copying it again, okay, u tau. Okay, and now we plug in all this inside, so there will be a 4/3 pi a cube, and then also this 4d pi rho. All this brings you this one, 4 pi d. Okay, this is from here. The rho, I will keep it inside the integral, and then there is also this prefactor, 1/4 pi a cube, which, okay, for convenience and to follow what is in the paper, I'm just copying in the way they put it, which is 3 divided by 4 pi cube. And then there is the 1/rho. Rho, remember, is r minus r prime. So this cannot be taken out of the integral. This is 1/r minus r prime. Okay, so the integral just tau 0 becomes this. And this is integral over the full volume. So in reality, what you can do, and this is also discussed in the reference, is that there is an analogy with electrostatics. So the first integral, this one, can be mapped to a problem in electrostatics. And the problem is the following. This is related to, okay, I write here an analogy with electrostatics. Be careful here because I didn't discuss, okay, I didn't discuss any electrostatics of this problem. I'm just saying that the integral that appears, this type of integral appears in electrostatics. Okay, so there's an analogy. You can go to an electrostatics or electronics book and find this integral solved there. It is related to the potential. Let me write it. It is related to the electric potential at R smaller than A of a uniformly charged sphere. Okay. I won't make this too long, but I just want to tell you that this integral, all this is equal. Okay, you see that I am integrating over R prime. So this, out of the integral, I should get something that depends only on R. Okay. So this is equal to 3 over 2a minus R squared divided by 2a cubed. Okay, all this integral. So this one is the most difficult one. I'm just giving you the result so we can go faster and then integrate over R. You see that the integral over R will be simple because there's just an R squared and this is a constant. So if we continue, what you get is the following. So we get now the integral over dv of this quantity, which is 3 over 2a minus R squared divided by 2a cubed. Okay, this is what I like to calculate. Now, remember this dv, okay, this is a bit intricate. I'm just doing now this integral, okay? This dv is the sphere of radius a, this one. So this volume, and be careful of something that this one depends only on R, but the sphere, the way we write the volume, reality is the solid angle. Okay, this will depend. You can also unfold it and put it with the theta, with the phi. And if I remember well, there was a sine theta here. Okay, this is a surface angle over the solid angle times R squared dr. Okay, this is the integral over the radial coordinate. And then we have 3 over 2a minus R squared divided by 2a cubed. Okay, just remember, so the integral of the solid angle is just 4 pi. So what you get out of this is there is a 4 pi. And then now, sorry, oh my God. Sorry, this 4 pi. This is the integral over this angle. And then we have to do integral R squared dr of 3 over 2a minus R squared divided by 2a cubed. Okay. So if you go on with this, the first integral is easy because it's 3 over 2a times R. If you integrate R squared, you get R cubed. So you get a cubed divided by 3, basically. So the first part becomes, okay, I think I have it here. Give me a second. So after everything put together, what you get is the following. So I'm going to wrap up everything because it's very simple. The first integral is integral R squared dr is, give me a second. Sorry, I made a mistake because, okay, remember one thing, that this is over the sphere of radius a. So the integral in R goes from 0 to A, okay? And this integral goes over the angle, so this is 0 to A. So this means that, okay, let me do it explicitly. This is 4 pi. The first term is 3 over 2A, and this is R cubed over 3, so it's A cubed over 3. And the other one is 1 over 2A squared, 2A cubed, an integral of R fourth, so it's R5 over 5, so it's A5 over 5. So what you get is A cubed goes like this, you get A squared, this goes with this, A squared, so it's 4 pi A squared, and then I get 3 with 3 goes away, so 1/2 minus 1/10, if I am correct. 1/10. Yes. Okay. So the first term is okay, I can write it like pi A squared. 4 divided by 2 is 2, and 4 divided by 10 is 2/5. Okay. So now I put the 5. This is 10. 10 minus 2, 8. So it becomes 8 pi A squared divided by 10. Okay. This gives us tau 0 almost, because I said that here I was integrating this, so I have to divide by 1 over 4 pi d. So tau 0 becomes 1 over 4 pi. Diffusion coefficient. This is the diffusion coefficient.
It is divided by 5, not 10.
Sorry?
It is 8 over 5.
Ah, sorry. Yes. Sorry. Thank you. This is 5, yes. This was my mistake. This is a 5, exactly. And then there is 8 pi A squared divided by 5. Okay, so this goes with this and gets a 2. This goes with this. So we have 2 A5 A squared divided by 5d. This is the value of the characteristic time. Okay, you see that the units make sense because the diffusion coefficient goes like length squared divided by time. So this formula makes sense in terms of the dimensions. Okay, so we arrive at the result we wanted, tau 0. So we want to compute this one. So now we know this. Then the variance becomes, this implies that the variance of mt becomes this one. Okay, let's go back. So it's twice tau 0 divided by t times the average of mt. So twice this is 4 a squared divided by 5t divided by time. Okay, this is tau 0 divided by t, and then the average of mt. Okay, this is the result I wanted to find for the variance. Okay. Okay, now we have the variance in terms of the mean. So we can compute the relative uncertainty, which was our main goal, the relative uncertainty in measuring the number of molecules. The relative uncertainty is, again, delta mt divided by the mean. So it's the square root of the variance of mt divided by the mean. So it's the square root of this divided by the mean. The first thing you see is that there is this prefactor. So there is, okay, give me a second because I don't find it now. Yes, there is this one. Okay, let me do it better. So we get this, something like this. So you see mt is here and mt is here with square root. So square root of mt divided by mt is 1 over the square root of mt. Okay, this. And the other is this factor, which is 4a squared divided by 5 dt. Okay, which I put it in the numerator. Now remember that I'd like to express this in terms of the real concentration. So the goal of this part of the lectures was to understand what is the time the cell needs to measure in order to have a given uncertainty, which I call this epsilon, when the cell is in a pool with average concentration given by C bar. So remember, empty. So I would like to express this also in terms of C bar, the real concentration. But this we know because we have this formula. So empty average is 4/3, so the volume times C bar. Okay, so then what we do is we come here and we just use that formula. So this will be the volume, 4/3 by a cube times C bar. And in the numerator, we have 4 a squared 5 dt. So this formula looks very, it's nice because it depends on a few parameters. We can take this out. We can take a square and have only 1a. And then the 3 goes in the numerator, the 5 goes in the denominator. So altogether becomes 1 divided by square root of 5 by dt a C bar divided by 3. Okay, and this is the key result I wanted to highlight. I put it in red. Okay, this is the relative uncertainty in terms of the time we measure, how long we have the cell measuring concentration, integrating, the size, so what is the region in which the cell is measuring the concentration, and the real concentration, which is this C bar. Okay, so this is a good estimate of what is the time we need to measure a given concentration with a given accuracy. Okay, so just to let you know that, just to compare with the previous model. So now we are getting something like, okay, we have to compare with, so in the previous lecture I said with a simple estimate I was getting this. The relative uncertainty was 1 over, if you go back to the notes you will see, 1.6 T C bar A. This was my simple estimate on the other day. Today I'm getting delta C over C bar. Okay, it doesn't matter if I put delta M or C because they are related by a constant, okay? Now I'm getting 1 over square root of 5 pi divided by 3. T is the same type of formula, T d C bar A, okay? So you see, this is the formula we got today. And this is the formula that we got on the other day with simple estimates. The most important thing for you to remind is that in both models, we get the same dependency with the parameters. So we get very simple estimate we are getting here, TDCA with the square root, and here also TDCA with the square root. So the only difference comes in the prefactor, which is good news because it means both theories give the same type of dependency. It's only a prefactor coming here, okay? And actually, this one is of the order of 0.55, this one, which is delta C divided by C bar. Let me call it this 0, okay? Which is this one. Okay, so in reality, this is not that much. This is not that much. It seems this is a 50% of difference, but it is not. When you have here, remember we did an exercise on the other day. The other day we said, I'm just checking, we had delta C over C when we had, for example, 90%, it was 0.1. And here, if you put 55, well, there is a change, but if you pass it to percentage, it's not that much. So what is important here to know is that this is a geometric factor but the key point is the dependency on chip. Okay, so if I go back into this, give me a second. So let me just show an application of the result. So an application will be the following. I'm taking this one as a more realistic estimate of the error, because I'm taking into account that there is time integration, etc. Application will be, it's so bad. Will be to determine the concentration with an root mean square error of 1%. Okay, in an observation time t. Okay, so I'd like to know how long do I have to measure in order to get concentration measurement of error 1%. Remember, 1% is delta C over C, 1 out of 100. Okay, so this means 0.01. Then from this formula, this implies that this is equal to 1 divided by square root of 5 pi divided by 3 times t C bar A. Okay, so from this formula, we learn that A, so let's say I have a fixed time t, so I'd like to know what is the radius in which I have to measure, what's A, okay? So I have a total time t, and I'd like to know over which distance the cell has to measure the number of molecules. So from this formula, I take squares. This is 1 over 100, so I pass it to the right. So I have 100 squared. In the denominator, I'll have the same thing, but without the square root. 5 pi divided by 3. Here I will have t d c bar, and I put it A to the left. Okay, this will be the size that the region in which the cell has to measure in order to have a desired 99% accuracy. So this is the same as saying 99% accuracy in a time t for measuring molecules with diffusion coefficient d. Okay, so this turns out 100 to the square divided by this number is around 2000 divided by t time diffusion coefficient concentration. Okay, it's there. All right. So, okay, I think with this, I have given you two types of models to measure the concentration. The main result you have to remember is that the error in the concentration measurement, okay, this is the standard deviation over the mean, goes like 1 divided by square root of the time you measure, the diffusion coefficient of the molecules, the real concentration you would like to measure, times the size of this region where you are taking measurements. Okay, this is a knowledge that we learned from these two models. Okay, and remember what we are discussing is okay, we have the cell, it could be a bacteria, and it can measure in a radius, in a sphere of radius A, the amount of molecules near its cell body. Okay, and I think well, I had another model to explain you, but I don't think I will have time today in half an hour to give it to you. I can send it to you the notes. I think it's interesting because it's about photoreception, but up to now we have discussed a lot of models. So for me, I will think the course is over. So I'll say here the end by now. All right, and I hope this was useful for you. You learn a lot of techniques and different models. In biophysics, this is obviously not everything. So I discussed ion channels, polymers, molecular motors, and now cell sensing, but there are many other, well, also run and tumble a little bit. There are many other interesting biological processes I didn't talk about, but they are equally interesting, and they are also nice models, like, for example, cell division, endocytosis, development, tissue dynamics, cell fate decisions. There is really a lot of fascinating topics to investigate and study. Okay, this I'll try to put in the exam, so you get to know different systems in biophysics. And okay, I'm open to your questions, and I think probably I'll okay, I leave you the stage for any question. Keep it to the recording if there is something interesting from your side. If not, we will end up here. So any question, doubt, ideas? I'm sorry if the sound wasn't good, because they are doing construction works all the time today here. And it's very difficult for me to focus with this. No questions? Okay, so if there are no questions, I'll